Hello, my name is Ryan and welcome to CS188 exam prep number 3. Today's topic is game trees and I'm just going to dive right into the worksheet. So for starters, this problem considers a game tree, but with a slight modification where we have the addition of certain nodes that give the successor with median utility right here. And so what does that mean? Well, we have these little pentagons right here. And for each of these pentagons, we say, okay, if we have values of 3 of its children, let's say 1, 2, and 3, then the median utility node is going to choose the value with the median utility. So the median of 1, 2, and 3 is 2. So the value that would get propagated up is 2. And given this scenario, given this modification of the traditional game tree, we want to ask ourselves, is it possible to prune any of these nodes, any of these leaf nodes in the tree? And the question asks us to consider any possible pruning scenario where they don't have to necessarily be pruned at the same time, but is it possible for the leaf node to be pruned at all? And note that this is a little different than alpha beta pruning just because we have some sort of edge case nodes right here that act a little differently than normal. So we can't just run an algorithm. We kind of have to think about how the bounds of the different nodes change as we assign values to different nodes. So let's get started. For part A, it's asking us to look at the first 4 nodes in the tree. So right here. And the question asks, okay, can we prune any of these nodes? Well, let's consider the fact that the left median node right here with 3 children, to prune any of the values or to get any of the values for that median node, we need to guarantee that we know at least 2 of the children's values first, since one of them is guaranteed to be the value of the median node passed up to the final maximizer, right? Because if you consider how the median node works, we know that if we have any 2 values, then knowing a third one allows us to choose one of those values in between. And so really the only information that we can, the way that we process information from the median node requires us to know at least 2 of the children here. And for this case, none of the nodes in part A can be pruned because we need to know the value at this node and we need to know the value at this node in order to do anything special. And in either case, we would have to look at V1 and V2 along with V3 and V4, just because knowing V1 doesn't let you prune V2 because it's just a minimizer, and knowing V3 doesn't let you prune V4 because that's also just a minimizer. So in this case, the answer is none. All right, so let's consider part B. In part B, we have these 2 values right here, and we assume that we know their values because we determined that we can't prune them, so we have to look at them. So let's define min1 as the value of the first minimizer, min2 as the value of the second minimizer, and min3 as the value of the third minimizer. Well, let's think about the case where we might not need to know the final value of min3, which is where we could potentially prune the remaining nodes. So the reason that we wouldn't have to necessarily know the final value of min3 is because we could be able to put a bound on the median node's value after exploring only partially at that tree. And then from there, we could determine the value of the median node as either being like min1 right here, min2 right here, or some minimum of min1 or min2, or just something like that, where knowing some values in the subtree of min3 allows us to come up with a bound on the value that the median node can take. So let's suppose we put an upper bound on min3 by exploring this left subtree right here, v5 and v6. So in the case that the maximum of v5 and v6 is going to be less than both min1 and min2, that means that the value temporarily at this subtree is already going to be less than min1 and min2. So in this case, if we know that this minimizer is guaranteed to return a value that is less than or equal to both min1 and min2, we know that the median cannot possibly be anything returned from this subtree because it's already smaller than min1 and min2. And so the median that gets returned is going to be the minimum of both min1 and min2, and it completely ignores the subtree of min3. Therefore, we can say that we can definitely prune v7 and v8. because we don't need to look at their values in order to determine whether or not what value gets returned to the median node in certain cases. Okay, now let's see if it's possible for us to put a lower bound on min3 instead. So let's say v5 is larger than both min1 and min2. So I'm going to erase this part. And let's say v5 is larger than min1 and min2. Well, in this case, if the minimizer chooses the left subtree, we know that min3 right here, this value, is always going to be greater than or equal to v5, which is also always going to be greater than or equal to the maximum of min1 and min2, right? So if we have that sort of bound on our subtree, then we don't necessarily need v6 to get the correct value for the median node, since whatever it is will also be larger than min1 and min2. And if it's always going to be larger than min1 or min2, then we would essentially be able to select min1 or min2 as our median immediately and not have to look at v6 at all. And if the minimizer chooses the value of the right subtree, the value at v6 is still unnecessary because the minimizer never chose that subtree. Instead, it would be choosing a subtree, it would be choosing the value at this subtree. So regardless, in this scenario, v6 doesn't really matter. And we don't need to look at the exact value to know the range. Therefore, we can also say we can prune v6. All right, so let's move on to part C. So part C is given these 4 nodes right here, and we want to see, okay, whether these can be pruned as well. So just for consistency with the solutions, I'm going to assume that the value that gets propagated up to this node after exploring the whole left side of the subtree is z. And I'm also going to denote these 3 minimizer values as min1, min2, and min3. So just for clarity, I'm going to get rid of all this. All right, great. So now we're looking at the left subtree of the right half of the tree. And we want to see, okay, whether or not we can prune any of these nodes. So let's assume that the highest maximizer node right now with the value of z and with these min1, min2s, and min3s. So in this part, we could consider the scenario where min1, which is this value, is less than or equal to the maximum of v5, v6, which are these nodes right here. Oh, sorry, not v5, v6, v9, v10. I misspoke. Which are these nodes right here, right? And let's assume that's also less than or equal to z, which is the value at the very top of the tree. In this case, we can now realize that if either min2, which is this node, is less than or equal to z, or min3 is less than or equal to z, then the value of the right median node of this node right here is going to be useless, right? Because if we have that bound of everything is less than or equal to z, then we know that the median can't possibly also be greater than z. Because if we have 2 values here that are less than the value at the top maximizer node right here, the maximizer is going to want to choose the current value instead of anything that the right subtree can produce. Therefore, only if both min2 and min3 are greater than or equal to z will the whole right subtree have an effect on the highest maximizer. But in this case that I'm talking about, the exact value of min1 is not needed. And it suffices just to know the bound over which, like, whether we are less than or equal to z or greater than or equal to z. And in this case, essentially, since we only need that bound, we only need to know the first value that gets returned from this tree. So anything from this side that gets propagated to the minimizer. We don't need to know necessarily v11 and v12 because that's not necessary to determine that bound. So in this case, we can eliminate v11 and v12. And going off what we were saying earlier, we can move on to part D, where if we think about how we can guarantee that no values in this right subtree get propagated up to the root node, the root node, we can see that if min1 is less than or equal to z, so if this first node was less than or equal to z, and min2 is less than or equal to z, so I'm just going to write this for clarity, min2, min3. If min1 was less than or equal to z and min2 is less than or equal to z, we can immediately stop. And so in that case, we can realize as soon as we explore this v13, right, since this is a minimizer, we're going to get some bound on what the value of min2 can be. As soon as we explore this node, we'll be able to tell, okay, in that case, maybe both min1 and min2 are going to be less than or equal to z, so we can immediately stop and prune the remaining nodes. Therefore, all of these other nodes right here are irrelevant in this case. And then we could potentially prune them if we know some other bound given min1 and min2's approximate values. Therefore, I can say I can also prune v14, v15, and v16. All right, and that's the end of problem 1.